The title of the paper ID 684 is exploring classification of histological disease biomarkers from renal biopsy images. This paper is jointly presented by Medas Labs, IIIT Delhi, and Arcana Laboratories. Kidney diseases kill more than 1 million people every year worldwide. End-stage kidney diseases receive little efforts for their prevention. In most cases, it is diagnosed in very late stages. Artificial intelligence, especially deep learning, can be used for automating the kidney biopsy assessment to make the diagnosis cost-effective and accessible. Glomeruli are the primary filtration units of the kidneys. Any change in the structure of the glomeruli may act as a potential indication of its abnormality. On the other hand, diseased kidney tissues form a scar on healing, which is called fibrosis. A healthy glomerulus is considered normal, while a diseased is termed abnormal. Alternatively, the percentage of scarring in a biopsy image can tell the extent of the disease. In this paper, we present two datasets pertaining to digitized images of glomeruli and fibrosis, called the RJD and RFD respectively. Both these datasets are under the collective hood of RGFH database. The dataset statistics are as follows. Anonymous biopsy images were procured between January 2018 to July 2018 through the Olympus camera and digitized using Motic EasyScan 3 at 20x. The RGFH database was extracted from a pool of archived renal whole slide images. All the tissue samples were cross-annotated by multiple pathologists, and an expert kidney nephrologist verified the annotations. The following slide shows the data augmentation techniques used in the process of classification. We used CLAHE for histogram equalization as it reduces the amount of noise that is augmented. The following slide shows the framework of transfer learning architecture. The input to the system is the pre-processed image, while the output is the prediction of the class. 3 fully connected layers are appended that are kept trainable, and others are freezed with their respective weights. This slide shows the results of glomeruli and fibrosis classification using ResNet 50, Inception v3, Inception ResNet v2, and VGG19. The ResNet 50 architecture shows the best performance. The given slide shows the framework of a supervised classifier with feature extraction using pre-trained transfer learning methods. Basically, the last layer weights of the neural network model are used for feature extraction by convolving with image pixel values. Image vector so formed is used as input to the ML classifier. The following two slides show the results for the above architecture. Empirically, image features from Inception ResNet, followed by classification using logistic regression for both glomeruli and fibrosis classification performs the best. The next slide depicts the framework of multi-gaze attention network. Essentially, tissue-level discriminating features are localized instead of being in the entirety of the image. One possible solution is the unsupervised feature extraction approach using attention-based deep learning strategies. MGNet uses multi-headed self-attention, in which 3 attention maps are generated over the whole slide image through residual skip connections from the initial ConvNet layers in parallel. Each of the 3 attention maps is appended and the scaled dot product is computed. The model jointly appends to the information from different representations. The next 2 slides present the chief observations of the paper. ResNet 50 architecture records an accuracy of 72.35 and 66.87% accuracy on RJD and RFD datasets. Logistic regression implemented with features extracted by Inception ResNet v2 outperforms transfer learning methods. MGNet architecture records the best accuracy of 87.25% and 81.47% on RGD and RFD datasets. To conclude, feature extraction with supervised learning gives better results than simple transfer learning. Multi-headed self-attention CNN models can be used to improve the results for both the classifications. Thank you.